All right, so there's a question on entropy here. So remember, entropy means disorder. So it can be individual S or change in entropy. Okay, so we're going to compare two items here, and we're going to determine which one has more entropy. So here we're looking for if there's a, this is a change, and if the change leads to more disorder, then the entropy, or I should say if the change delta S leads to more disorder, then it's positive. If it leads to more order, then it's negative. All right, so we have two items here. We'll determine which one within it has more entropy. Is it going to be 1 mole of oxygen gas or 1 mole of HNO3 nitric acid? Okay, look at the states here before you make a decision. Okay. So which will have more entropy, more disorder? Okay, obviously the gas will, because gases have more microstates. That's the term. Have you heard of this term, microstates? Okay, more rotation, more vibration. They just have more motion, and that implies within them more disorder. All right, 3 moles of N2 gas versus 2 moles of N2 gas. Which do you think has more entropy? Okay, more implies more disorder. Okay, so more moles, it's the same N2 gas, but there's just more of it. Okay, 1 mole of NaCl solid. A solid is very, very ordered. If you look at a solid under the microscope, or an atomic microscope, or whatever, look at the arrangement. Okay, it's very, very ordered. They're called unit cells. And aqueous is solute, which is NaCl, and solvent, which is water. So, which would have more stuff in it? More stuff would mean more entropy, and that would be not the solid, but the aqueous. Okay, solid would have, very, very, it's very ordered, so very minimum entropy. How about milk at 25 degrees or milk at 37 degrees? Okay, higher temperature, more microstates, more motion, and more disorder. And then calcium phosphate solid or sodium chloride solid. So here we're going to look for more mass. Okay, if there's more mass, then there's more entropy. So which one has more mass? I think calcium phosphate has more mass. Okay, there's just more atoms, 3 calciums, 2 phosphoruses, and 8 oxygens. So this is going to have more mass and more entropy. Okay, so what are we looking for here? Gases will have more entropy than a liquid. Okay, solid is the most ordered. We're looking for more mass, higher temperature. All of these things contribute to an increased entropy. Okay. Are there any questions on this? Okay, so make sure you circle the one that has more entropy. All right, let's do our final set of problems here. Calculate E cell for the following reaction. Notice it's E cell and not something else, not E standard state. So if it's non-standard state, we're going to use the Nernst equation, which is given here. And we have this notation here. It's going to be anode, couple. Okay, the salt bridge is 2 lines. Cathode, couple. And that is the Nernst equation. So let's translate this. Let's translate this into a chemical equation. Anode, magnesium going to magnesium plus 2. Okay, magnesium going to magnesium plus 2. many electrons and where should we put it? Okay, we're going to put 2 electrons in the product side. This is the anode from the anode couple. So what is the anode here value for this magnesium losing 2 electrons? Let's get our sheet out. 2.317 volts. Positive. Do we have to flip it? We have to flip it. So is it positive or negative? Positive. Okay, so make sure you flip this one on the sheet. Okay. And then we have Sn plus 2 going to Sn solid. Okay, how many electrons and where? 2 electrons on the reactant side. Well, obviously, if this is the anode, this just by default has to be the cathode. And what is that number? Here you don't. 0.14. Okay, very good. And how many electrons are being transferred here? Okay, this is a 2 electron transfer reaction. Negative? Okay. Okay, don't flip whatever you see on that because, right? So, negative. Okay. So don't flip it, whatever's on the sheet you do that. This you flip the sign, the anode. This is a 2 electron transfer reaction. Okay, and let's do this here. So 2 electrons cancel. So we're going to get we're basically going to get this. Okay, magnesium solid plus Sn2 aqueous. And this is going to go to Sn solid plus magnesium aqueous. Okay, so what's 2.317 minus 0.14? 2.23 volts, and this is E cell. Okay. So this is the E cell that's going to go to this go here. So now we will use this equation. We're almost done. E cell. Trying to find the right pen is always a challenge for me without spilling everything. E cell is equal to E standard state cell, which is 2.23 volts minus 0.0257 volts divided by N is 2, natural log of Q. Okay, Q here is Mg plus 2, products over reactants Sn plus 2. Alright. So we know here the magnesium concentration is 0.24, and the Sn plus 2 concentration is 2.4. The magnesium concentration is 0.24, and then the Sn plus 2 concentration is 2.4. So what is this, 1/10, I think? Let's get our calculator here. Anyways, let's do this on our calculator. I didn't bring my calculator. Do you have a calculator I can borrow? Thank you, Allison. let's do it together. Maybe it's right. I don't know. Sounds right, actually. 0.24 divided by 2.4. 1/10. I'll natural log it. Okay, natural log the answer. Is that times a minus. Okay, check it out. There's a minus here in front of the numerator. Minus 0.0257 times negative 0.0257. Okay, divided by 2 plus 2.23 plus 2.23 and 2.26, okay, which is our answer. Volts. Okay, so this is what E cell is. That is a non-standard state. Okay. Go ahead, you have a question?
So for Q, when you're putting it in the log,
Natural log.
yeah, not in the natural log, I know that it's products over reactants, right?
Yep.
So why does magnesium go as a product? Like, how can you tell it's a product?
These are the reactants and these are the products. So it's
Like both of them.
This is magnesium solid, and this is magnesium plus 2. This is magnesium. First of all, solids don't go in.
Oh.
Solids and liquids don't go into the thing. Yeah. You never put solids and liquids in Q or K. Solids don't have a concentration, Leslie. They have a density, so we can't put moles over liter for a solid. Okay. All right, that's good. Anything else before we move on to page 5? All right, let's move on to page 5 here. Looks like it's kind of the same thing, so we'll do that. Yes. All right, calculate delta G naught for the following. Is this page 5? Page 3. Did we do page 3? Yeah, we did page 3. Okay. All right. Calculate, okay, so problem 14 on your test will be similar to this. Calculate delta G naught for the following reaction. And that's the Gibbs free energy. We'll utilize this equation. F is called the Faraday constant. All right, how many electrons are being transferred in this reaction? So we'll go from 2Au to 2Au plus 3. 2Au solid goes to 2Au plus 3 aqueous. Okay, I don't know if you know this, but you can actually cancel out the 2's. Okay, you don't have a copy?
She doesn't have a.
Oh, that's weird. I'll give you this when we're done. No. Oh, here you go. So you can actually, like in math, you can actually divide both sides by 2, cancel out the 2's, and you'll get Au solid going to Au plus 3, just like you can in a math equation. Okay. All right, so how many electrons and where? 3 electrons on that. Is this the anode or the cathode? We lose 3 electrons, so this is the anode. And what is that on our calculator, in our sheet? Okay, I see it here. Okay. Okay, positive 1.50, but what should we do? We should flip it to negative 1.50 volts. and then we have 3 calcium going to calcium solid. You can cancel out the 3's. You'll cancel it out. So this 3, like in math, can cancel out with that 3. So, so for this half reaction, we have calcium plus 2 aqueous goes to calcium solid. Okay, and 2 electrons are going to be here. This is the cathode. And what is that on our calculator? Negative 2.87 volts. Negative 2.87 volts. So this looks like it's not going to happen. The delta G will be positive. Why will the delta G be positive? Because E cell is negative. Okay, if delta G is positive, we call that an exergonic reaction. It requires energy. An endergonic reaction, excuse me, an endergonic reaction. It requires energy for it to move to the product side, and this is a battery that's not moving in this direction. It minus 4.37 volts. And our net reaction is, okay, we're going to multiply this one by 2. Okay, and we're going to multiply the bottom one by what number? Okay, so how many electrons are being transferred here? This is a 6 electron transfer reaction. So we're going to have 2 AU solid plus 2 calcium aqueous goes to 2 AU plus 3 aqueous. Actually, this 3, right? 3 calcium. So 2 AU plus 3, and then 3 calcium ion, and then 3 calcium solid. Okay, the 6 electrons get transferred. So, you know, we just regenerated the original equation, by the way. The original equation in the problem. All we did was split it and then added it back to get the original equation. The only difference now is that we have a voltage, and that's negative 4.37 volts. Alright, so that is E cell. F is a constant. N is, as you guys mentioned, a 6 electron transfer reaction. So we can go ahead and solve for the Gibbs free energy at standard state. How many electrons are being transferred in this reaction? 6 electrons. So now we'll use our equation. Delta G is equal to minus NF E cell. Okay, so minus N is minus 6 moles of an electron. Faraday constant is 96,500 joules over volts. E cell is negative 4.37 volts. The negative and negative make it a positive, so delta G being positive makes it an endergonic reaction. And then what do we have here on our calculator? So the minus and minus is plus, so 6 times 4.37. Okay, times 96,500. And that is our joules. I'm going to divide it by 1,000. 2530 kilojoules. So yeah, this Au, which is gold and calcium don't make a good battery. Okay, unless you flip it. If you flip it, it's positive 4.37 volts. Alright, let's do this in galvanic cell notation. The anode and the cathode. So anode, one line Au plus 3. Okay, and then the cathode is calcium plus 2, one line calcium solid. Okay. But this is not a reaction that is favored, okay, minus 4.37 volts. Instead, you probably want to flip it to make it positive 4.37 volts. In that case, when you flip it, you know, the roles change. This is the cathode, and this becomes the anode. Okay, if you flip this, actually, no, what you want to do is flip the bottom one. You want to flip the bottom one so you get a positive voltage. So this becomes the anode, yeah, and that has to become the cathode. So you flip them both and flip this entire reaction to make it positive 4.34 volts, 4.37 volts. But that's okay, don't worry about that. This, the way as it is configured right now, is negative voltage, and it's a positive free energy, which is an endergonic reaction, and it's not favoring the products, it's favoring the reactants. To get it to favor the products, what I've been trying to say is that you need to flip this. Okay, make this the cathode and make that the anode. Okay, so I think that is mostly what you'll see on the exam. Let me give you one more thing here. Let's just review this quickly before I end class. We have delta G is equal to delta H minus T delta S. It's the same thing also in standard state. Okay. So a reaction that's going to be favored regardless of temperature. Okay, a reaction that's favored regardless of temperature, high temperature, low temperature, medium temperature, any temperature. That type of reaction would be enthalpically favored, in which case the delta H is minus. Imagine putting a minus sign here. And entropically favored. Okay, that would be a spontaneous reaction, more disorder. Imagine putting a positive here. So if you put a positive delta S and a negative delta H, no matter what, negative minus multiplied by a positive, no matter what temperature, it's going to be, the delta G will be negative. Okay. So this would be enthalpically favored and entropically favored. All right, on the flip side, let's say they're disfavored. If delta H is positive and delta S is negative, okay, imagine putting a positive sign here on delta H, and imagine putting a negative sign here for delta S in this equation. Well, the negative and negative become a positive, and a positive with the positive delta H will be positive no matter what temperature. So this is enthalpically not favored, entropically not favored, because if you plug in a positive here and a negative here, no matter what, you'll get a positive delta G. So delta G will be endergonic, okay, meaning positive at any temperature. But then we have these strange scenarios where it's enthalpically favored, okay, but entropically disfavored. Okay, so here you got to do some thinking here. If your delta H is minus and your delta S is also minus, so minus into a minus is positive. So you need to get that temperature as low as possible to keep the minus dominating in your delta H, which in turn will make your overall delta G the final judge. a negative. Okay, because we want a negative delta G with a minus delta H and a minus delta S. Keep this as low as possible so that the delta H remains minus. Because remember, minus into a minus is plus. Okay, minus into a minus is plus. If this is going to be minus, to keep delta G minus, you want to lower the temperature. So here what you want to do is lower the temperature to make delta G exergonic and favor the products. Okay, you're going to plug it in here to these equations, to this equation. Okay. So we say this situation is when it's enthalpically favored but entropically disfavored. Entropically not favored, disfavored. Okay, and then the final situation is where your delta H is not favored, that's enthalpically disfavored, endothermic reaction, but it is entropically favored, that's positive. Okay. So you imagine putting a positive here, and you put a positive here for delta S, you put a positive here, and a positive here. To make the overall delta G negative, what do you need to do? Okay, you're going to ramp up the temperature. Okay, so here you raise the temperature T to make the delta G negative, okay, which is what favors the products. An exergonic reaction releases free energy and it favors the products. So you're going to raise temp T here to make delta G exergonic. So that's some multiple choice questions on the exam. Are there any questions or comments here? If you want the reaction to move forward towards the product side, yes. Okay, so thermodynamics is all about will this reaction favor the products in terms of energy? So yes, you want your delta G to be negative to favor the products, because a negative delta G will release free energy. And that actual free energy can be used if you take a biochem class or maybe a biology class. That negative free energy from the delta G, called exergonic, can power other reactions in the cell. Maybe it can power, muscle movement or a cilia to move, or all these things. Or, something. Another reaction that can't go, it can go with the free energy released with a negative delta G. Reaction that has a negative delta G. Okay, so that is a review for the test. So we have one more lecture on Monday. I don't have anything planned, so I was thinking of just canceling class on Monday, if that is okay. Is everyone okay with that? Provided you study this video and the video on Wednesday, I think you should be okay. So how many of you want to cancel class on Monday, or how many of you want to have class on Monday just as a question and answer period? Because I don't have anything planned, and I think I went over the test fairly well. All in favor of canceling class? Raise the hand. Everyone, it's unanimous. Wow. Okay, unbelievable. Okay, so you do not have to come to class on Monday, but do come to class to take test 4 and quiz 4, which is the following Monday after Thanksgiving. Okay. All right, have a good, happy Thanksgiving then. I will see you not next week. Take care. Bye-bye.
So it's